20,000 people lost their lives in 2011, and hundreds of thousands of homes were completely obliterated when a tsunami 50 feet in height struck the coast of Japan. This catastrophic event left the international community in a state of profound shock and mourning. Why was such a high price paid in human lives and infrastructure? At first glance, the natural defense systems of the time seemed sufficient. But in reality, the sheer force of the water overwhelmed every existing barrier, proving that a much more massive and sophisticated engineering solution was required to prevent a repeat of the disaster. Japan initiated the construction of a colossal tsunami defense wall, spanning nearly 250 miles along its vulnerable eastern coastline. But this is just the beginning. The process is only gaining momentum as the scale of the task demands unprecedented resources and precision. One can notice how tens of thousands of engineers and construction specialists are mobilized across the shoreline to manage the logistical complexity of the project. To construct barriers reaching heights of 50 feet, they utilize world-class machinery capable of pouring and shaping millions of tons of high-strength concrete. It is visible how the heavy equipment moves with mechanical rhythm, positioning steel reinforcements and enormous blocks that must absorb the kinetic energy of the ocean. Each section of the barrier is calibrated down to the last millimeter to ensure structural integrity under the weight of millions of tons of rushing water. Everything only gets more complicated when considering the long-term effectiveness of such a massive undertaking. The process does not end at the completion of the physical structure itself. One big question remains regarding whether this concrete Great Wall can truly provide absolute protection against the unpredictable tsunamis of the future. The structure stands as a testament to human engineering and resilience in the face of nature. The massive concrete panels now line the horizon, where the barrier meets the sea in a quiet, gray expanse. 4 massive tectonic plates converge directly beneath the Japanese archipelago, creating a geological junction of extreme instability. Why does this specific seafloor location generate more than 500 earthquakes every single year? The answer lies in the constant grinding and slipping of the Earth's crust as these plates collide under immense pressure. But this is just the beginning. When these geological plates shift suddenly beneath the ocean floor, the entire seabed can rise or sink within seconds. This sudden deformation of the Earth pushes up enormous volumes of water, creating tsunami waves dozens of feet high. These waves accelerate toward the shoreline with the concentrated force of millions of tons of water. One can notice how the ocean surface seemingly transforms into a solid, moving wall. In previous decades, residents of small coastal towns instinctively ran toward high ground the moment the Earth began to shake, responding to red alert warnings broadcast over loudspeakers. At first glance, these precautions seem sufficient, but in reality, the scale of natural forces can exceed any historical precedent. March 11, 2011, provided the most devastating proof of this persistent danger. A magnitude 9.0 earthquake ruptured more than 300 miles of a tectonic plate boundary deep under the Pacific Ocean. The resulting tsunami reached heights of nearly 50 feet, far beyond any defense mechanism the nation had ever prepared for. It is visible how such a volume of water can bypass any standard obstacle. That single wave took more than 20,000 lives and flattened over 120,000 homes. The disaster triggered a catastrophic crisis at the Fukushima nuclear power plant. It gets more complex further on. Existing seawalls had been designed only for waves up to 26 feet, causing them to be completely overwhelmed as the water surged over their crests. Japan quickly recognized that while the earthquake caused the initial damage, the tsunami acted as the primary destroyer of the coastal infrastructure. Nearly 250 miles of tsunami defense walls now line the northeastern coast as a result of this realization. Each structure stands between 45 and 50 feet tall, with heavy foundations plunging 80 feet deep into the ground. Everything only gets more complicated when considering the engineering required to anchor these massive concrete barriers. The government invested more than $12 billion not only into the construction of these walls, but also into the complete upgrading of emergency alerts and evacuation routes. One can notice the precision of the new concrete blocks, forming a continuous line against the horizon. The equipment gradually moved millions of tons of material to ensure the foundations reached their required 80-foot depth. This concrete Great Wall is designed to buy precious minutes for residents to reach safety before a wave arrives. It does not end at this stage. Automated sensors now link the walls to centralized warning systems that trigger the moment a plate shift is detected. The process of fortification serves as a physical commitment to preventing a repeat of the 2011 tragedy. The massive structures stand silent and ready, marking the completion of this phase of coastal protection. 14 meters. This is the minimum required height for the colossal concrete barriers designed to shield the Japanese coastline. Why is such an immense scale necessary for a structure that remains dry for decades? At first glance, a wall is a simple physical obstacle, but in reality, its geometry must counteract the fluid dynamics of a multi-ton surge that behaves more like a moving wall of earth than water. The process begins not with concrete, but with the systematic analysis of every data point recovered from the 2011 disaster. Engineers meticulously reconstructed the destructive force of the waves within specialized artificial wave tanks. One can notice how hydraulic actuators push the water to mimic the exact frequency and velocity of the historical event. These scaled-down models allow the team to observe how the liquid mass hits the surface and eventually overtops the barrier. It gets more complex further on. The research phase does not end at this stage. Scientists continuously adjusted the thickness, the vertical slope, and the overall height of the wall based on how the miniature models responded to varying pressures. It is visible how the water creates a vacuum effect and a massive lateral push that could easily topple a standard structure. To counter this, the design moved toward a wide trapezoid base that lowers the center of gravity and distributes the weight more effectively. Only after the models demonstrated peak performance did the engineering team finalize the technical blueprints. The foundations are driven 20 to 25 meters deep into the earth to anchor the structure against the immense kinetic energy of a surge. These deep piles ensure the wall is not pushed over or undermined when the water levels rise past the top edge. Everything only gets more complicated when considering the internal structure. A reinforced steel core provides the necessary tensile strength to prevent the concrete from shattering under impact. The final specifications call for a height of 14 to 15 meters, creating a massive shield capable of withstanding the most extreme geological events. The design phase successfully concludes, providing the foundation for the massive construction efforts that follow. 400 kilometers is the total length of the massive coastal defense line spanning the Tohoku region in northeastern Japan. Why was such an immense distance selected for a single unified project? After the catastrophic events of 2011, engineers determined that only a continuous barrier through the prefectures of Aomori, Iwate, Miyagi, and Fukushima could provide the necessary protection. This stretch now represents the longest and most integrated defensive fortification in the history of the nation. Crews began the process by clearing the designated route of all remnants from the previous disaster. One can notice how hydraulic manipulators systematically remove destroyed infrastructure, power lines, and old pipelines to create a clean corridor. But this is just the beginning. Logistics hubs and concrete mixing stations were established immediately along the coastline to ensure a constant supply of materials. Because the rainy season in Japan can halt most industrial activity, workers installed temporary drainage systems and specialized crane platforms to maintain the pace of construction regardless of the weather. It looks outwardly simple to prepare a site, but in reality, the proximity to the ocean requires constant monitoring of the water table. Engineers focused their attention on the weak, sandy soil that characterizes much of the Tohoku coast. It seems simple to build on the shore, but in reality, the weight of the structure requires massive ground reinforcement to prevent sinking. They drilled detailed geological surveys before driving deep concrete and steel piles into the earth to find stable strata. Layers of crushed stone and sand were added and then compacted using heavy vibrating rollers to create a base that will not slide or crack under the weight of a wall tens of meters tall. Excavators dug foundation pits that reached depths of more than 20 meters in specific sections. Near the shoreline, crews built temporary cofferdams to keep the seawater from flooding the active work zones. The process is only gaining momentum. Once the pits were cleared, a base layer of concrete was poured to serve as the platform for dense steel reinforcement cages. These foundation blocks are built with an extremely wide footprint to ensure the wall cannot be overturned by the massive kinetic energy of a surge. Workers assembled thick rebar cages above these foundations. following the precise specifications developed during laboratory testing. One can notice how the formwork is positioned before concrete is pumped into the molds in a continuous stream. Each block, typically measuring several dozen meters in length, undergoes a strict cycle of pouring, curing, and inspection. These individual sections are then connected to one another to form a single unbroken barrier along the Pacific edge. Specialized energy-dissipating units like tetrapods and delos are installed on the ocean-facing side of the structure. These concrete blocks are stacked in multiple dense layers at the base to break the initial force of a wave before it ever touches the main wall. Everything only gets more complicated as the terrain changes. Some sections utilize stepped faces or sloped surfaces to reduce the height of water surges, while the landward side is reinforced with crushed rock and drainage channels to prevent the accumulation of rainwater. The top of the wall often serves a dual purpose as a public walkway or a local roadway for the town. Railings and safety ladders are integrated into the final structure to allow for safe access and maintenance. Transition to the next level. Because the project spans nearly 400 kilometers, engineers made minor adjustments to the design to account for variations in coastal depth and soil composition without altering the core architectural principle. Interlocking precast concrete blocks were added to the outer surface in areas requiring extreme impact resistance. One can notice the crane lifting these panels into a tight, uniform pattern that functions as a reinforced armor layer. This protective skin is designed to withstand decades of constant erosion and the relentless pounding of the Pacific Ocean. Special entry points had to be engineered for busy port cities like Iwaki to allow for uninterrupted maritime traffic. The first solution is a top-down tsunami gate consisting of a massive steel panel suspended between two towering concrete pillars. It only looks obvious to leave the harbor open, but in reality, these gates must close in minutes. Driven by hydraulic motors and pulley systems, the steel panel drops vertically during a warning to seal the entrance completely. Japan also utilizes bottom-up rising gates in harbors, where overhead clearance is restricted. Under normal conditions, the entire gate assembly lies flat on the seafloor, allowing ships to pass overhead without any obstruction 24 hours a day. When sensors detect an approaching tsunami, a hydraulic system pivots the gate upward from the seabed until it locks into the sidewalls. Because the mechanical components remain submerged, they are manufactured from highly corrosion-resistant steel with fully sealed hinges to resist the pressure of seawater and sand. The material is ready to serve as a permanent shield for the coastal communities. 400 kilometers is the total length of the continuous coastal defense system stretching along the Tohoku coastline. Why was such a massive engineering undertaking necessary across this specific expanse of Japan? At first glance, the scale of the barrier seems insurmountable, but in reality, it serves as a calculated response to the devastating kinetic energy of the Pacific Ocean. This structure now stands as the largest defensive maritime wall ever constructed in the history of the nation. The project required a financial investment exceeding $12 billion to reach completion. Engineers, geotechnical specialists, and construction workers, totaling more than 30,000 individuals, were mobilized to execute the technical plans. One can notice how thousands of units of heavy-duty machinery operated without interruption for a period of 5 to 7 years. The process is only gaining momentum as various sectors of the coastline were addressed. Hundreds of wall segments rose simultaneously along the shore, each demanding a unique approach to its structural integrity. Depending on the specific characteristics of the local terrain, specialists applied different foundation treatments and reinforcement techniques to the concrete segments. It only looks obvious to build a uniform wall, but in reality, the subsurface conditions required constant adaptation of the reinforcement steel and casting methods. The equipment gradually moved from one completed section to the next, ensuring the barrier remained unbroken. Everything only gets more complicated when considering the sheer variety of soil densities encountered over the 400-kilometer stretch. Simulation data indicates that the operational seawall system reduces the impact forces of a tsunami by 30 to 50%. These precious calculations translate into several additional life-saving minutes for coastal residents to reach higher ground during an evacuation. This time frame is sufficient to protect tens of thousands of people during a Level 1 tsunami event. One can notice how the concrete face of the barrier is designed to break the initial surge of the tide. But this is just the beginning of the protective measures integrated into the regional infrastructure. Fishing ports, coastal roads, and residential districts that suffered total destruction in previous events now exist behind this reinforced perimeter. The presence of the wall significantly lowers the probability of catastrophic damage when high-magnitude waves strike the coastline. It does not end at this stage, as the barrier functions as a primary shield for the vital economic assets of the Tohoku region. The camera glides along the top of the massive structure, showing its integration with the surrounding landscape. This 400-kilometer barrier represents the final line of physical defense for Japan against the most destructive natural forces on the planet. Although the system is not designed to stop every conceivable type of tsunami, it provides the country with a technical foundation for resilience and increased confidence. The project concludes this phase of coastal fortification, leaving behind a landscape transformed by $12 billion of engineering precision. The massive concrete sections remain in place, ready to dissipate the energy of the ocean and secure the future of the communities living in their shadow. 73,000 tons is the massive weight of a single reinforced concrete segment used in the construction of Japan's underwater transportation arteries. Why is such immense mass necessary for structures resting on the seafloor? One might assume that lighter materials would be easier to maneuver during the sinking process. But in reality, the extreme buoyancy of a hollow tunnel requires every ton of this weight to counteract the upward displacement force of the displaced seawater. Engineering in an environment completely isolated from the atmosphere demands unwavering precision as geological conditions change with every meter of progress. In the modern world, these underwater tunnels represent a crucial component of infrastructure that connects distant islands and spans deep bays. One can notice how these constructions create breakthroughs in mobility, where bridges or ferries can no longer accommodate the volume of transit. The process is only gaining momentum as these routes become vital economic arteries for busy port cities. Detailed geological surveys and meticulous preparation serve as the foundation for ensuring safety under the crushing pressure of the seabed. Engineers drill into the subsea topography to collect soil samples and analyze rock strata. This allows the team to determine bearing stability and identify latent hazards that could compromise the structure. Environmental considerations remain a priority throughout this initial phase. It is visible how the project team assesses potential impacts on marine ecosystems to ensure natural habitats are disturbed as little as possible. Transition to the next level involves active environmental protection. Noise mitigation measures are implemented during construction to shield marine life from industrial vibration. Technicians may even install artificial reef structures to provide new habitats for local species. But this is just the beginning. The actual construction phase utilizes the immersed tube method to assemble the tunnel from prefabricated sections. Each standard element measures approximately 217 meters in length and is manufactured on land with near-perfect precision. Inside these massive segments, several distinct compartments are designed for specialized functions. One can observe two main chambers for highway lanes and one dedicated strictly to a railway line. A separate service corridor is integrated for future maintenance and inspection duties. Floating pontoons and specialized cranes transport these sections to the open sea once they are complete. The equipment gradually lowers the segments into pre-dredge positions on the seabed with millisecond control. Each segment is joined sequentially to form a continuous path of the required length. The most critical phase of this operation lies in the execution of the joint connections. If the seals are not handled with jewelry-like precision, seawater infiltration could lead to catastrophic structural failure. Rubber gaskets are inserted between the segments to establish a watertight barrier. Simultaneously, layers of sand and gravel are placed above and around the tunnel to provide stabilization against buoyancy. Only after the connections are securely locked and stabilized are the temporary end bulkheads removed. Everything only gets more complicated when dealing with strong turbulence or complex underwater terrain. In such environments, the immersed tube method becomes impractical due to the difficulty of anchoring. This technique is specifically suited for areas with a stable seabed and gentle water currents. Once the structure is sealed, the focus shifts to the internal safety systems and operational assessment. Many modern projects utilize a two-level design to double traffic capacity without expanding the external structural footprint. Drivers maintain a stable speed of 60 kilometers per hour while passing emergency exits positioned every 200 meters. Engineers conduct rigorous tests on waterproofing integrity, pressure resistance, and fire safety systems. Ventilation performance and structural stability are verified under maximum load conditions. Maintenance is what truly determines the longevity and safety of the tunnel after it opens to the public. Technical teams conduct regular inspections of the concrete lining and the waterproof membranes. They search for any signs of deformation or cracking in the support frames and drainage systems. Hundreds of sensors installed along the length of the tunnel continuously monitor pressure, temperature, humidity, and vibration. Real-time data flows to a central control room where engineers analyze the earliest signs of structural fatigue. One can notice specialized vehicles equipped with high-pressure water jets and suction systems performing periodic cleaning. These machines remove sediment and keep the tunnel floor clear to prevent blockages in the drainage network. Through the integration of advanced sensor technology and manual maintenance routines, these tunnels operate safely for many decades. The molten stream of logistics and transit continues through the ocean depths as a testament to engineering resilience. The material and the structure reach a state of equilibrium with the surrounding environment, and the construction phase concludes. 120 meters of depth is the technical limit reached by the undersea tunnels that now traverse the Japanese seabed. Why are these coastal fortifications and deep water passages engineered with such extreme durability? To the eye, a concrete seawall appears to be a simple static barrier. But in reality, every cubic meter is calculated to withstand the immense kinetic energy of a tsunami wave. These massive megastructures represent the peak of maritime engineering across the island nation. One can notice how the reinforced concrete structures rise dozens of meters above the shoreline to protect vulnerable coastal zones. This process is only gaining momentum. Automated sensors and heavy-duty floodgates operate in a continuous state of readiness to seal off inland areas from the ocean. The equipment gradually monitors the structural integrity of every seawall and tunnel segment. Japan demonstrates how advanced engineering can be synchronized with the unpredictable forces of nature. But this is just the beginning. It is visible how the nation focuses on the resilience of its infrastructure following every major seismic event. Engineers implement seismic isolators and deep-sea reinforcements to ensure that undersea tunnels remain stable during tectonic shifts. Transition to the next level. Huge hydraulic systems and massive breakwaters are positioned along the coast to dissipate the force of the waves. At first glance, the construction of these barriers seems like a standard civil engineering task, but in reality, it requires a unique chemical composition of concrete to resist saltwater corrosion for decades. The material lays in an even layer across the shoreline, forming a protective perimeter that guards the population. Everything only gets more complicated as global engineering standards continue to evolve. Therefore, the study of these incredible megaprojects continues beyond the borders of a single country. Global industrial complexes are currently developing new methods to build similar structures in various geological conditions around the world. The process of exploring these large-scale technical achievements remains a continuous endeavor for engineers and researchers alike. Thus, the technical analysis of these ocean-facing fortifications reaches its conclusion, providing a foundation for understanding the next phase of global infrastructure development. The material is ready to move to the next processing phase without haste.